Good morning, students. Let us start with part 2 of chapter 6. Work done. This is our first topic of this lecture. If pressure of gas is P and external pressure is P ext. Ext means external. It's only a way of denotation. How to denote external pressure? This is P ext. Then force is equal to pressure into area. So work done is equal to force into length. So work done will be equal to pressure into area into length. So it will be negative of external pressure and delta V. Negative sign is placed to get the appropriate sign for work. So in case of compression, that is work done on the system will be positive, and in case of expansion, work done by the system will be negative. This can be represented in the PV graph as below. This is the graph. For reversible process, it can be written as W is equal to negative of taking integration of P external and delta V. Integration from Vi to Vf. Vi means initial value. Vf means final value. Now P external is equal to P plus minus dP. And W is equal to taking negative sign outside, putting the value of P external. P external means P plus minus dP into delta V. Now W is negative of integration Vi Vf P delta V. Now P is equal to nRT upon V. This can be represented in the PV graph. This is Vi, Vf and difference is volume V. Work done in isothermal and reversible expansion of gas. W is equal to minus nRT ln of V2 upon V1. W is equal to minus 2.303 nRT log to the base 10. This 2.303 is for natural log V2 upon V1. Now delta U is equal to 0 for isothermal process. So Q is equal to minus W. So answer will be 2.303 nRT log V2 upon V1. Now isothermal and free expansion of ideal gas. For isothermal expansion of an ideal gas into vacuum, work done is 0 as P external is 0. Since external pressure is 0, then U is 0 and Q is 0. For isothermal irreversible change, W is equal to minus P external delta V and Q is equal to P external delta V. Now here are some examples for you. Let us start with these examples. Example number 1. 5 liters of an ideal gas at a pressure of 10 atmosphere expands isothermally at 100 degree centigrade into a vacuum until its total volume is 10 liter. How much heat is absorbed and how much work is done in the expansion? How much heat is absorbed and how much work is done in the expansion when constant external pressure of 1 atmosphere exists? So try to solve this. Here external pressure is 0, W is 0 and Q is 0. And for the second part, as external pressure is 1, so Q will be minus W and it will be P external into Vf minus Vi is equal to 5 liter atmosphere. Okay, let us start solving second question. A sample of gas expands isothermally from 10 liter to 20 liter against pressure of 2 atmosphere. Calculate the work done. Here is the solution. As W is minus P external delta V, so it will be 2 into 20 minus 10. You are putting the values of delta V. Answer will be 2 into 10, that is minus 20 liter per minus 20 liter atmosphere. Now question 3. A balloon contains 10 moles of a gas in a volume of 5 liter and 27 degrees Celsius. Balloon burst so that gas expands against 1 atmosphere pressure. Calculate the work done by the gas and value of R is given. Now start with the next term, enthalpy. It is symbolized by capital H. Enthalpy is defined as total heat content of a system and is equal to the sum of internal energy and pressure volume work. It means H is equal to U plus W and W is equal to PV. So H is equal to U plus PV. It is state function. At constant pressure, we know that first law of thermodynamics says what? It says delta U is equal to QP plus W. It means QP is equal to delta U minus W. It means delta U plus P into P delta V. Put value of delta V. Delta V is what? V2 minus V1. And expand and open the bracket. And answer will be U2 plus PV2 minus U1 plus PV1. And it is equal to delta H. So change in enthalpy is heat absorbed or evolved by the system at constant pressure. Then delta H is positive. It means endothermic reaction. Delta H is negative. It means exothermic process. Relation between delta H and delta U. H1 is equal to U1 plus PV1. H2 is equal to U2 plus PV2. Subtracting these two equations, H2 minus H1 is equal to U2 plus PV2 minus U1 plus PV1. Rearranging the equation, it will come out to be delta U plus P delta V. Now let us consider a reaction involving gases. If V1 is total volume of gaseous reactants, V2 is total volume of gaseous products, N1 is the number of moles of gaseous reactants, N2 is number of moles of gaseous products, all at constant pressure and temperature. Then using the ideal gas law, we can say that PV1 is equal to N1RT, PV2 is equal to N2RT. Put the value in P delta, it will be obtained P delta V is equal to delta N RT. So enthalpy of reaction is delta H is equal to delta U plus delta NGRT. Now heat capacity. It is the increase in temperature of any substance. C is equal to Q upon delta T. What is molar heat capacity? It is the heat capacity for 1 mole of substance. What is specific heat capacity? It is defined as heat required to raise temperature of unit mass of substance by 1 degree. It means C is equal to Q upon M delta T. Let us derive relationship between Cp and Cv. What is Cp? At constant volume, molar heat capacity is Cv and at constant pressure, molar heat capacity is Cp. As as QV is equal to delta U, it will be CV delta T. QP is CP delta T, that is delta H. Now put the values in. Delta H is equal to delta U plus P delta V. It will be CP delta T is equal to CV delta T plus P delta V. Rearranging, it will become CP minus CV is equal to R. Thank you.